Hi, and welcome to part 4 in creating a DLX architecture simulator. Uh, in this video, we're going to continue on working through the state machine and work on getting it actually cycling through and quote-unquote executing instructions. We're not going to actually execute anything, but we will cycle through instructions, or stages rather, not instructions, stages. So, to start, let's quickly recap what we've done so far. So far we've handled the initialization of everything with a very basic initialization level. So we start off in main, we create a state machine. The state machine then creates a state and creates the registers. The state is just initialized to a very basic state of being in the instruction fetch stage with the value of 0, which we can see here for the instruction value 0. And then the registers are initialized by initializing a set of general purpose registers and a set of floating point registers, which are then put into the register. The registers here, I guess they're here actually, and then they're returned to the state machine. And then the state machine returns back to main, who will then execute the run function. We have a little bit of error handling in place, which we implemented last episode, and everything cleanly gets initialized right now. So that is that. So to start today, we are going to make some changes to something we just changed last episode. So previously we were using typedef unsigned integer uint for stuff like our registers. Now, this is nice, but we kind of get the terminology. The terminology starts being a little bit weird when we start using uint32_t. So what we're going to do is we're going to go back to DLX sim, and we're going to typedef those. So we're going to typedef three different things. We're going to have typedef uint 16t. And we're going to get some errors here while I type these out, but 32t and uint 64t. So a 16-bit integer is considered a half word. A 32-bit integer is going to be a word, and a 64-bit integer is going to be a double word. If you've maybe done this with other with C in other places, but I know that the Visual Studio Compiler has something you can include for a D-word value, which will give you a whatever a word is on your system. So a word is kind of like a base unit. On a 32-bit machine, a word is 32 bits. On a 64-bit machine, a word is 64 bits. On a 8-bit machine, a word is 8 bits. So it all depends on your machine as to how big a word is. And a word is kind of then your base I'm looking for your base unit size. So for the deluxe architecture, a word is 32 bits. So I figured, let's actually make these all capitals. So I figured it's best to use the word instead of uint32, so that we know kind of what is stored in them. So yeah, we shouldn't need to use signed words, but it's kind of just a way for us to keep with the naming scheme that is accurate. So let's now go in and change where we have these used and change them from uints to words. So uint32 will be a word. So put all of these to words. Oh, that's not what I wanted to do. I want to close that. So that was going to the actual header file. So yeah, there's no way to change all of these at once. So let's just change them one at a time. So there we go. We have words. I don't know if we'll ever need to use a half word, but we have access to it just in case. So I'm not going to change these because we are going to come back to these in a bit. We'll change this. And then in here, we don't have any. So now the next thing we're going to change is these instructions. So instead of having these bit fields, because bit fields can be, they're not always going to be as accurate as we'd like them to be. It's very implementation specific. So instead of having these structs for that, we are going to have a struct with a word in it. Actually, we don't even need that. We are going to have a word with our instruction. And instead of going through the process of like trying to decode it and insert it into a struct with its system, what we're going to use, we're just going to use bit manipulation and just shift in and out the values as we need them. So, for example, with this add instruction, we would shift right these 6 values, and then we would get the opcode, and then shift 5 and ignore them, and then shift 5 and get a register, shift 5 and get a register, shift 5 and get a register, and then shift 6 and ignore them. So that's what we're going to do instead of doing all this fancy structs and union stuff, because, well, bit fields are cool, they're a neat thing to use. They're not accurate enough for the way we want to use them, because the way I wanted to use them was to say, so you have word instruction, and then you have, I guess I have to have pointer. Anyways, you could use them still, but the bit shifting is a little bit nicer because it's like a bit field, except it's a little bit more accurate. And this way, we're not taking up twice the memory when we could just use just the instruction and then shift as we need things. So it just basically saves us memory, is what I'm trying to say. And who doesn't love bit manipulation, anyways? So now we have words, half words, and double words that we can use as data types, which is just a wrap around these unsigned integers. So now, what we're going to start working on is implementing the run state machine function. So, to start with, we're going to need, in our function here, we're going to need a setup, we're going to need a loop, and we're going to need a cleanup. So, to start, with our setup, we're going to need what's called and we're going to use a double word for this so we get a lot of space. We're going to need a cycle counter, which is going to count how many cycles our pseudo CPU has run through. Just for fun. There's no real. I can't see any need for it yet in the near future, but it's nice to keep track of, and you can kind of see how long your program's been running and all that kind of stuff. So we have a cycle counter. We'll set it to 0, and then from there we're going to need a loop. So we'll just write a for forever loop, and then in our cleanup we're going to run called destroy state machine. And now we have a for forever loop, and we need a way to terminate it cleanly. So there's no real way to do it yet. How we're going to do that will depend on our implementation of a few things. So we'll tackle that once we get to that. For now, what we're going to do is we're going to start by, let's actually switch this. Instead of a for loop, we'll switch to while cycle counter is less than, let's say for now, just 1,000,000. And we'll say temporary, or temporary. All right, that's better. And then what we'll do at the bottom here is we'll say cycle counter plus plus. So now if we were to run it, it would loop until cycle counter equals 1,000,000. So that is very simply our state machine's life cycle. Is it just counts through and it just loops and loops and loops forever. Now, what it does each loop is what it gets fun. So we have our state machine. Not our state machine, sorry, we have our state handler. So our state handler has a state, and the state doesn't do much yet. So each state has a function, as a stage, which is going to be the big thing, and then it's going to have all this other stuff in there. So let's go to statehandler.c, and what we're going to do is we're going to start implementing. So we have create, initialize, destroy. We're going to need to create some function declarations in here. So stage, we'll call it stages. So we're going to need void instruction fetch stage. Just trying to think what we should call it. I'll just call it instruction fetch for now. And we can't because that's a term up there. So let's go to function fetch stage, or let's say handle instruction fetch. And then, actually, do we want to do this in here, or do we want to do this? Let's create of one function. We'll call it void for now. We may have to add an int to return an error, but we'll leave a void for now. So void process state, and then we'll take in state as an argument, and that's what we will have the state machine call in here. So process state, and then we'll say state machine state. So that's going to run and go do that, and then inside our state handler we will have void process state state s. So now in here we're going to need some stage functions. So we're going to have void fetch, void decode, void execute, access memory, and write back. And right now we'll just have these as void return value and void parameters. And we will switch state, s current stage, and for each case, case instruction fetch, we will call fetch, and then break, and then case instruction decode, we will call decode, case instruction execute, we will call execute, and then what are the other ones here? We have memory access and write back. Access memory. Really had an extensive that process, that one. And then I guess write back will be an error because we have write back there and write back here. So let's call it something else. Let's say actually, let's do this instead. Let's change these to all capitals. So that way we, since this is case sensitive, we can use these words or these literals many times, these string literals. So now we can have write back there and write back here. So all of these though will need to be redone. Luckily they're all in this file. Fetch and then we have decode, and then execute, and then memory access, and then write back, and then break. So that's our state processing. We just say, if it's one of these ones, call the function for it. So now let's write out these functions really quick. Void decode, void execute, void access memory, void write back. So that's it right now. That's all it does. So inside each of these, let's just print inside fetch. Just so we know which one we're in. And then inside execute, and then inside access memory, and then finally inside write back. Okay, so now each of those will just print where they are, just so we know. So instruction fetch is going to call fetch, and so since we only have one function or one state right now, we could actually just fall through to each of these and then exit out and then come back and do it again. But that's not really the best way of doing things because, well, it's a fine way of doing things. There's nothing wrong with it. It's just we want to be prepared for when we have multiple cycles. So what we're going to do is we're going to say, once you're done fetch, set the current stage to be instruction decode. So this is basically incrementing to the next stage. And it's the it'll work out the exact same way as following through, except that we'll only fall through once this state gets passed in again, meaning that if we pass the first state in, it'll go instruction fetch, or it'll go instruction execute, and then set to memory access, and then return. And then the next instruction will come in, it'll do decode, and it'll set its current stage to execute, and then it will return. And then the next state will come in, and it'll do its fetch, and then set its to 1. So it's just a way of just incrementing the state, and yeah, it works the same way as following through, except that we can be prepared for when multiple happen. So if we were to now, and the reason we're incrementing it in here instead of in this function is that we don't have to pass it. We don't have to pass the state around many times. But now if we run this, it'll print all 5 just like that. So it's kind of hard to see. So let's pause it and open it up, and you can see we have inside fetch, inside decode, execute, access memory, write back. Fetch, decode, execute, access memory, write back. So it's effectively looping through the process that it's supposed to. So inside fetch is the last one, so if we were to continue and keep going. So let's close that. Actually, let's stop it. So that's how it's going to loop through. That's the exact process it's going to do, so it's doing exactly what we need it to do, except just printing instead of doing anything. So at this point, our state machine is finished. Our state machine is done. It is everything it needs to be. So at this point, this is the point where we can start implementing our instructions. So let's start by just using a dummy instruction. So what we'll do is we will start with fetch and then execute, or I'm going to delete all these prints. So what we'll do is we will have, let's see, what we're going to need to tackle first is how we want this to operate. So the nice thing about the deluxe architecture is it is bi-endian, meaning it can be big endian or it can be little endian. So if you're unfamiliar with what endianness is, that's a really weird term, so I'm going to spell it out here. So you can, if you're unfamiliar, if what I say next isn't clear, you can at least look it up and know what to search. So we're talking about endianness, and big endian or little endian. So our instructions are, oh, these are all tabbed wrong now because let's tab these all over. The joys of tabbing things over to look nice and then changing your tab spacing. So 31 to 0 is what all of these use. Now, here I have it written in little endian. Yes, I think. Yeah, this is little endian. Sure, I think. Yeah, it should be little endian. Someone can correct me if I'm wrong, but I'm pretty sure that's it. Yeah, that's it. Yeah, little endian. I guess though it doesn't really. No, yeah, that is little endian. So yeah, after much debate, anyway, so little endian is most significant bit goes in 31. Least significant bit goes in 0. And then in big endian, your most significant bit goes in 0, and your least significant bit goes in 1. Now, which is your most significant and which is your least significant? I guess it doesn't really matter. But we can essentially decide whether we want 0 to be on the right or 0 to be on the left. So do we want our most significant bit, which is bit 0? Yeah, because what this will determine is whether we read our numbers in from left to right or if we read them from right to left. So if we're reading them from right to left, that's little endian. And if we're reading from left to right, then it's big endian. I'm just gonna double check this with a value really quick. So if we have 1, 2, 3, 4 in big endian, this would be our most significant bit would be in position 0. So in this one, our most significant bit equals 1, and our least significant bit equals 4. Big. And then in little endian, it's our most significant bit equals 4, and our least significant bit equals 1. Yeah, so it depends on how we want to read it. So we want to read our numbers left to right. Now I'm just confusing myself. Right, so we have our our values 31 to 0, 31 to 0, 31 to 0. Now, how we actually want to, we're going to represent this with 31 being the leftmost bit and 0 being the rightmost bit. Exactly how this is represented here. So let's go to our state handler, and we're going to use pseudo operations for now, just to kind of make this work and kind of demonstrate how an instruction will go through the process. So we'll say fetch. So fetch is going to return a word, and that word is going to be the instruction. Yeah, instruction equals. Now, this would be read from the file normally, but what we're going to do is we're going to set it to whatever our instruction is going to be. So let's change this to word. So if we go to DLX sim and we look here, we can't really copy that. So let's just dock it to the side here. And then for now, minimize that so we can see both of them. So, and have a decent amount of space. So we have our first 5 bits, our first 6 bits are zeros. So 1, 2, 3, 4, 5, 6. And then our next 5, so let's write out, here's our instruction. Instruction is add our source, register 1, so R1, R2, R3. Now when we write this assembly, we have to determine what order we want the operations in. Do we want RD, RS1, RS2, or do we want RS1, RD, RS2, or R1, RS2, RD? We can have these in any order. For now, we're going to have it RD, RS1, RS2. Actually, let's see if we can quickly find what order they put them in the actual code. Let's see. We have, none of these say the actual assembly. Okay, so it is RD equals, or this is, yes, the first one is RD, the second one is RS1, and the third one is RS2. So exactly like that, which is pretty standard amongst assembly languages. There are a few that are weird, but most of them follow that standard. So we have 6 bits for zeros. So our source 1 is register 2. So that's going to be 5 bits to write down 2. So it'll be 1, 2, 3, 1, 0. Our next 5 bits are going to be our second source, which is 3. So 1, 2, 3, 4, 5. The next 5 are going to be our destination. So 1, 2, 3, 4, 5. And then we're going to have 5 unused. 1, 2, 3, 4, 5. And then we're going to have our opcode, which is 0x20, which is 1, 1, 2, 3, 4, 5, 6. I have all the instructions written out in a spreadsheet with their description, their opcodes in hex, decimal, and binary, and their format, and then also what they do in a pseudo C. So I'll put that in a description so that it's easy to find and you can look at that and reference it. But that's our instruction. So that's what fetching is. It's a very simplified fetch, but it is exactly what we need it to do. So that's a very big number. So that's what it is. It's add R1, R2, R3, where R1 is the destination, and R2 and R3 are the sources. So now let's what we need now is we need to decode this. So our decode is going to have to, so this is where we might need a struct for our instruction. So let's, yeah, so we might actually need one now. So let's type def struct instruction. So I guess I could have kept it. So, maybe this is where it would have been good to keep those that we had before. But then again, what do we... Actually, what we can return is a void pointer. Maybe. Let's first see. Let's see what we get back. So let's have... let's just use words for now. So opcode equals... Well, now see, here's the thing. If it's R-type instruction, the opcode's going to be the last numbers. If it's not, it's going to be the first numbers. So that's a very weird way of implementing it. We're going to need a way to determine which kind of instruction it is. I guess we'll have to start by shifting the first 6 bits out. So I think it's the first 6 bits regardless. Yeah, so the first 6 bits regardless. So we start by decoding, so we're going to need to pass in a word instruction. So return instruction. So here we go. Let's say word actually, let's go current s instruction equals fetch, and then let's pass in s instruction. So let's set this now to take in a word. So let's say word. Let's change it to I, so it's shorter. So now, let's say, yeah, let's do short, I guess, for now. uint 8t. So just for now, because we only need 6 bits, let's say opcode equals I shift left 6. So what that's going to do is it's going to say take the left 6th most bits, which is going to be all zeros, and shift them. Actually, let's do one more. I guess we can't, because there's unsigned, which is 2, or signed, which is 2. Oh, sorry. Right has 2. So right, you can do 2, which is a sign shift, and a no, maybe. Yeah, they don't want you to do that here. So 2. So we shift 2, and we put the 6 bits shifted into opcode. So now if actually, let's not call it opcode. Let's call it uint 8t. Let's call it. Actually, let's call it opcode for now, and we'll say it's I shift 6. So now if opcode equals 0, that means we are R type. Otherwise, we are I or J type. So what we can do is we can call jump table opcode and then pass instruction, and it will have the rest of the parameters. However, if it's R-type, we're going to need to shift a lot more. So in this case, we want the last 6. So we have 6 out of 32, meaning there's 26 left. So what we can do is we can say I equals I shift 20, and then opcode equals I shift 6. So this will say, actually we don't have to assign it to anything. We can just do I. So we can shift left 20, which will give us no, we don't want to do that because that's gonna actually, yeah, because instruction will still be passed. No, we don't want to do that because yes, let's do this. Let's do word instruction equals I. So let's manipulate instruction instead. So instruction, and the reason for that is now when we pass I, we will have everything except for the 6. Or we'll have everything. Actually, no. Let's undo all that. Because, so, here it's fine if we get here, because we'll be passing in the remaining 26, which will be source 1, destination, immediate value, or value. For this one, what we want to do is we will say opcode equals right shift 6. So this will put the right 6 values into opcode. So actually, I just looked it up and the syntax is wrong. What we want to do is we want to go opcode So actually, let's actually experiment with this. So let's, because I'm not entirely sure what's going to happen here. So let's go printf opcode %d, because yeah, I'm not entirely sure anymore. So let's print I and then opcode. So if you run this now and then pause it and flip back, so we have it's still 0. So that's not what we want at all. Because that means opcode's not getting any. Actually, no, it's not true. Opcode could be 0. Let's try shifting right. Or actually, let's shift left. Let's set this to a 1 at the beginning, which will make it a big number instead of. So it's still 0. So that's not it at all. So let's try opcode equals I, opcode left shift equals 6. So now let's try that. Well, that's still not working. So we're passing the instruction, returning this large, obscenely large number. let's see. This is not doing what we want it to do at all. So let's say word opcode equals 10 opcode shift 2. So let's run this and see. So we get 10. Okay. So now let's try shift equals 2. This should make it bigger. Yeah. Okay. So now let's make it smaller. Perfect. Okay. So that works. So let's go opcode equals I. Let's go I shift equals 6. Let's try that. So that should make opcode equal to a very large number. Almost. Let's say it equals I shift 6. Haven't done bit manipulation in a long time. Printing in binary. Let's see what that is. Apparently you can do U. Let's see if that's it. No, it's not it. I thought there was a way you could use like you could with hex. Yeah, let's do hex, I guess. Because that should be, yeah, that's wrong. So what that's doing is that's not shifting out 6. It's just giving us the 6 less. Because we want it to equal 32, or 20 in hex, rather. So that's not right. So that's not pushing the 6 out. So let's see. So, So 4 bits is equal to 1 1 hex value. So if we wanted to get the opcode, we'll use different bitwise operations. What we'll do is we'll do the first 4. So we want 1, 2, 3, 4, 5, 6. And then the rest can all be zeros. So if we have 32 over 4, we have 8. So we need 1, 2. So this gives us the first 4. And then 1, 1, 0, 0 is 12. So B 0, 0, 0, 0, 0, 0. So if we use that, because that's 1, 1, 1, 1, 1, and 1, 1, and then the rest are all zeros. If we take that and we take I and 0x and we AND that, it'll give us the opcode. Or it won't. I don't know why it didn't. Why is this not working? Actually, let's try 1, 2. Let's try it at the end. Now that's interesting. So this might actually be in reverse in memory, which kind of makes things a little bit inconvenient. So let's take a look here. Hex to binary converter. So let's open up a hex to binary converter, and let's print instruction. And now let's pause this, and then let's copy this value. So 861040, and convert it to a hexadecimal value, or a binary value, and we get, no, we do get exactly what we have written. Or do we? We have 4, 8, 12, 16, 20, 24. How many do we have here? We have 1, 2, 3, 4, 5. So that's right. And then it has 1, 1. How am I going to get? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33. Huh. That explains a lot. So let's try this again. We have, and let's stop this. So we have 1, 2, 3, 4, 5, 6 as zeros. And then we have 5 for the register, which is source 1. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So let's split these right now. So we have 6, 5. And then we have register 2. 1, 2, 3, 4, 5. And then we have destination, 1, 2, 3, 4, 5. And then we have unused 5, 1, 2, 3, 4, 5. And then we have opcode 6, which is 1, 2, 3, 4, 5, 6. So we have 12. We have 32 now. So we have 6, 5, 5, 5, and 5 is 26, and 6 is 32. So let's remove all these spaces now. And let's save that. Let's run that. And let's make sure we get the right value now. So it's different now. Now it's 430820. So if we convert that, we now get, let's stop this and go back. We get 2, 3, 4, 5, 6. 6 times 4 is 24. So that's 24. So we get 5 and 1. So it gives us, in sets of 4, so we get that. No, we get that, 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 and that. So yeah, well, these are not included in the converter. But, so that means that we are getting what we want now. So now, if we remove all these spaces and run this again, and now we pause this, we can see that we're getting our opcode now. Like we should. So 20, like we should. Okay. So now that we've got that sorted out, that was such a small error of adding one too many bits, and it completely ruined everything. So that's the importance of bit manipulation. So we're doing from the left, which is exactly what we want, because that's our opcode. So just to make sure that shifting wasn't working, let's try right shifting 6. Let's see what that gives us now. So that gives us 20 as well. No, 10C20 is not right. Because 10C20 is a very big number. So that's not right at all. 1, 2. Because yeah, shifting is just the number of bits we want to move over. Yeah, it just shifts it over the number of positions. Yeah, so that's, yeah. Yeah, so just moves it the number that we have specified. So that doesn't look like it works. Because if I think I'm right, that's moving everything over 4 to the right. Or actually, that's giving me that. No, that's not it. It's saying it is this, that. Okay, so what it is giving me is it's giving me, so if we were to shift left 20, I think that would give us the right number. So this is actually a lot more complicated than I thought it would be. Yeah, that's not working at all. Okay, so let's just go back to using the AND. So if we AND FB 1, 2, 3, 4, 5, 6. So we'll write that in for op. We'll create some constants here. So let's go to state handler. Actually, let's leave it up here. For our bitmaps, I really don't know what to call them. Let's create them. So we have R type flags bitmaps name question mark. So we'll have define unused actually that's not good. We'll call it opcode. And it's going to be 0xFC, not FD or FB, whatever I'd written before. It's FC 1, 2, 3, 4, 5, 6, 7, 6. Okay, so that would be the first 6 bits. So this is for R, I, J, and then we'll have source reg 1, which could be a flag. I don't know what to call it really. So 0x 3e, and then the last one, so it's going to be for R and I. So we'll change it actually to instruction. And then we're going to have define source reg 2 flag, and this is going to be 001F. This is going to be for R. And then we'll have dest reg R flag, and this is going to be F1. This is going to be for R, and then we'll have dest reg I flag, which is going to be the exact same as source 2. And I. And the only reason we're going to have a source reg 2 and dest reg I flag, even though they're the exact same, is just so when we're actually writing the code, it's easier for us to tell what's what. So that might actually go these might actually move yet. So I don't know if I want them in this actual file right now or not. We'll leave them here for now. So then we'll have unused, R unused flag, which is going to be for the 5 unused. So that'll be 1, 2, 3, 4, 5, 7C, R, and then we'll have R opcode flag, and this is going to be 3F. And then we will have I immediate flag, which is going to be 1, 2, 3, 4, 4 Fs. I, and then we're going to have finally J value flag, which is going to be 0x, 03, and then Fs. So those are our ways of getting. So let's just put G opcode flag. No, let's leave it at opcode flag. I like that better. So now if we go here and we go I and opcode flag, what this is going to do is it's going to take every single bit and AND it to all the bits in our opcode flag. So if our instruction is what's up there, and we have 6 and then all zeros, if this value in the and this value are 1, it'll be 1. If not, it's 0. So it just performs bit manipulation on all of these up and down, and it just lets us have just the opcode flag, which isn't what we want after all, now that I put some thought into it. It's actually not what we want, because the reason it's not what we want is because what we want is we want just the opcode chunk in the opcode here, because that's what we're going to use to actually call. We're going to use that to index the jump table. So what we need to do is we can go if I and opcode flag, so we can still use that. So if this equals 0, it's going to be false, in which case we'll go down here. So if it's 0, that means that it's R-type. If it's not, that means it's I or J type. So we're kind of a bit of a mess here, but that's okay. So we have so if it's R-type, that means that our so let's go word opcode equals 0. So if it's R-type, opcode is going to equal I and R opcode flag. If it's not R type, then opcode is going to equal this is going to get confusing because we're using the names wrong. But what we can do is we can say opcode equals I, and opcode equals opcode right shift 20 and our opcode flag. So what that is, and let's print opcode now. %x opcode. So what this is going to do is I just got to make sure that yeah, this should be fine. So this should actually not need this. This should be the same with or without the anding. So yeah, so this should do is this should set everything before opcode to 0 inside of opcode. And what this should do is this should give us just the first 6 bits and set the rest to all 0 anyways. Yeah, it doesn't work that way. So there should be one. It should give us zeros, but it might give us 1. I don't know for sure. Let's find out. So this should give us just 20 right now. So let's see. 20. Perfect. That's right. Now let's comment this out for now. And let's say word instruction equals, and let's do add I. So 0b 0 0 1 0 0 0, and then the rest can just be 0. So we have 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and then let's just copy those. So perfect, we're 2 shorter, which means we're right. So now this one should not be in here. Instead, it should go in here, and it should give us a value of add I 8. It should give us 8. 200. So that's not right at all. Oh, we should shift to 26. We want the first 6. 8. Yeah, so there we go. Okay, that's how we want to do it. So now let's try doing this and see if I changes. Alright. So let's go here and print F. Actually, let's run this and then pause it. And let's take that value and let's put it into a hex to binary converter. And let's make sure, let's see if we get the same value out that we could put in. So 2, 1, 2, 3, 2, 1, 2, 3. That gives us 0, 0, 1. Perfect. That's exactly what we want. So we don't need to do this, and we don't need this, And that's fine, yeah. Because otherwise we'd have to shift 20 to push it to the left, and then shift 26 or shift 26 to push it to the left, and then shift 26 to push it to the right, which would get rid of everything. So let's just do that right now. That's perfect. So if we have, let's put a comment here, add I. Let's just delete that. So to summarize what's going on here, we pass our instruction into decode, and decode checks what type of instruction it is by checking the opcode flag, which is a misleading term, but if it is 0, we get false, in which case it goes down here and it's an R type. And the last 6 are our opcode. So we can actually delete this unused. We're not going to use that. It's not necessary to have it. And then it says, okay, we have our opcode as this value. And then here we can call jump table opcode, and then there we go. So it checks. It says, what are the first 6 bits in the number? If they are zeros, we have an R type, and our opcode is the last 6 bits. If it is not 0, it's true, and our opcode is the first 6 bits. So let's define ij opcode offset is 26. So that'll never change. There's no real reason for us to have a constant other than to say ij opcode offset. So it just gives us a way to use words instead of actually, just let me put ij in front. I'll just put opcode offset. So I don't know. That's kind of, I think in this case it's explanatory enough. So there, we would call that, and then actually this would be instruction func. So we would return, and then that would go into, so s instruction equals decode, and then this is instruction func. So this then returns the function to call, so we don't want to actually call it, and then that would be what's called an execute. So we would do in here instruction func if, and go if, and we can set that here, s instruction, and then up here s instruction, or instruction func. Let's take these and put them up here, and we'll change this to bit manipulation constants, and let's just comment out the ones we're not using right now, so we know that we're not using them. Oh, well, it should be pretty self-explanatory, but let's just do it anyways. That one, there. So right now we're using those 3 values. So can we not take, oh, it's an if, that's why. Func. Okay. So can't use a keyword as a variable name. So there, that is effectively how we are going to handle that. The next thing would be to implement the handling of data and passing arguments around. So how we want to do that yet, I'm not sure. We may just pass it in as a word, and then we would have the first 6 bits all zeros, or the first 16 bits all zeros. So we have a couple options, a couple ways of doing it. Again, we can look at what options we have when we actually implement this, because it's going to be 3 different ways. So actually, let's look at that right now. So let's go to state handler. Actually, let's do it in here for now, because I don't think we need it anywhere else. If we need it somewhere else, we'll move it somewhere else. Data type declarations. So let's do a type def union onion, and we'll call it data. Actually, let's do, yeah, it's called data. So for our type, we are going to need 5 for the source 1, plus 5 for source 2, plus 5 for source 3, or for destination. So that's 15. So that's half word. So h word, r type, r type. I type is going to need 5 for register, 5 for register, 16 for immediate value, which is 26. So we're going to need a word. So I guess regardless, we're going to need a word, because they're all going to use different. So we don't need a union, we just need a word. So let's pass in a word with the data. Now, we'll have a word with the data, so we'll set the first we'll set it based off what we're going to have. So we'll need to return because we would want data to be let's pass in now how do we want to do this? Maybe this one, we just pass in the state, and then we set the data in the state. Unless we go decode function, or opcode, and then we change this to decode opcode, and then we have word decode data, args. And we have, let's go to state handler. Yeah, let's go type def enum instruction types, and we have r type, I type, j type, and then custom for when we implement custom ones. So we're going to have decode arg, or decode data. We're going to need instruction type. Let's change that to type. And instruction type. And word with the instruction. And we're going to return a word with just the data in it. So decode instruction, or decode opcode rather, and then we're going to call s data equals decode data, S instruction. Oh, it's not instruction. Let's go back to state. We have function is what we want. And we're going to have word data. So this should actually be function. And then decode data. Void decode data. No, word decode data. We're going to have instruction type IT and word instruction. So let's call this type. Yeah, so we need a way to tell the instruction type. That's a good thing to know. So let's not even pass in the instruction type. Let's remove that for now, because we have no way of telling that actually until because instruction type. We're going to have to know by, so we're going to have word, actually let's pass in the opcode. Word. Actually we can use an H word to kind of save on space. We still have to do it here again. So H word. Actually, let's return opcode and change this to H word and change this to H word. And then this is going to be jump table decode opcode. And then what we can do is we can say decode data H word equals decode opcode, or opcode equals decode opcode instruction. This should be those brackets. Okay, so now we have the opcode. And then what can we use to now know what we need for instructions? Actually, we can just say word data equals, and this is going to make sense in a little bit. We can say it equals instruction shift 6. We don't even need opcode for that. We can just say the data is instruction right shift 6. No. We can say it is instruction data flag. Mask, that's the word, mask. Our opcode mask and opcode flag, opcode mask. We won't need these. Don't need this comment. Won't need this one. So we'll still call these bit manipulation constants. These are masks. That's what they are. Haha. So opcode mask, our opcode mask, and then this one is going to be instruction and opcode mask, or data mask. So now the reason for this is, we can actually just return this. So, I guess that's not really necessary to have a whole function for this, but it's okay. So this is going to return, this is basically going to say, we're going to set the first 6 bits to 0 and give you the remaining bits. And then we're going to pass data as an argument to the function. So if we go back now to our, this can go here. If you go to our instruction handler, this is not going to be a void pointer. It's going to be a word. And now we will pass in instruction and data mask. Let's put this in brackets so we can just make things very super explanatory. So this is a tiny function, but it's necessary. So now execute's going to take in s data. And we'll put a word in here. So this is going to take and give us the last 26 bits of the instruction as the data. And then the function is going to process data however it needs. And we don't have to worry about trying to figure out if it's an R type or an I type or a J type. It's going to have what it needs no matter what type it is. So just like that, we are now handling functions. So that is most of our process for decoding instructions. It was kind of messy to get through, but we are working on a bit level, so it's kind of expected. So I'm just going to go over this again, just to kind of make sure everything's explained properly. So we have our state and our state machine, and the state machine says, okay, we're going to come into our cycle, our loop, our forever loop, and we're going to process the current state. Once we have a multi-cycle data path, it's going to be SM state 0, and then SM state 1, and each state is going to get processed in turn. And it's going to be quote-unquote at the same time, but it's in turn. So it says, okay, process our state. And the state says, okay, we're going to go here, and we're going to check which stage we're in. So we start off in fetch, and it goes down to fetch, and it will read the instruction from our file, whatever it is. But right now it's going to be just a constant value, and it's going to return that instruction. So this would be like fseek4, 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 and just read 4 bytes of data. And it's going to return that, and it's going to say, okay, so in our state, we're going to set the instruction to be that, and then we're going to set the stage to be decode. And then it comes back, goes through the cycle again, says, okay, now we're in decode, so we're going to pass the instruction to decode opcode, where we check to see whether it's a I type, or a I type, J type, or R type. If it's I or R, we take out the last 26 bits, and we give the first 6 bits to the opcode. So this one gives the last 6 bits. I guess it depends what you view as first or last. It gives bits 31 through 26, 31 through 26, 31 through 25. 31 through 26 are given to opcode. It says, okay, if it's an R type, we're going to give bits 5 through 0 to the opcode. And then it returns the opcode, which we're going to use to index into our jump table. And then it goes back up and says, okay, now we need the data. So we're going to take the instruction, and we're going to take the last 26 bits and use it as the data. So if it's an R type, that means the first 6 bits, which are unused, are not passed in. If it's the I type or J type, the first 6 bits, which is the opcode, aren't passed in. Either way, it's the 6 bits we don't need. And then it returns, goes through the cycle again, says, okay, now we're going to be in execute. So we're going to pass in the instruction. Actually, this should be function. So we're going to pass in the function, and we're going to pass in the data. And then what we're going to do is we're going to call that. And that's it. It's just going to call it, and that's it. And then wherever our function is located, it's going to process the data. So it's going to know whether it's an R-type, I-type, J-type function, because we're going to put that in there. We're going to say function add, and we're going to say, okay, these 6 bits are going to be our register 1, these are going to be register 2, and these are going to be the destination register. So we'll be able to handle that inside of our function. So we can have like instruction handler can have like R-type handler, J-type handler, and I-type handler. So anyways, then we're going to come back and set the next stage to memory access. And then we're going to go, okay, case memory access. Boom, we're going to go call access memory. Then we're going to return, change to write back. And then we're going to go back in here. We're going to say write back, call write back, and then we're going to set it to instruction fetch. And then we'll loop all the way back to the beginning and start all over again. So the confusing stuff is definitely all this masking and manipulating data on a bitwise level. But it is pretty easy when you just sit down and kind of work through it. It might have been a bit confusing when I explained it, but it is what it is. That's just how it happens to be sometimes. It is pretty simple. I may not have made it seem that way, but it is pretty simple once you take some time to look at it. So, but that's what we're going to cut it short now. Next time we'll start working on actually implementing all of our instructions as functions, so we can start calling them. So we're getting closer and closer and closer to being done our state machine, at which point we'll be done stage 1. So we're actually very close to being done stage 1 of this software, and at that point we will get to the more complicated part. But until then, happy programming.